let's just review quickly what we remember from capacitors. This is my circuit, and I close the switch. What happens?
Capacitor charging.
The capacitor charges. So we could then, but it takes time to charge. So we're looking at, if we don't have the capacitor in there, and we close the switch, well, we just have a certain amount of current in the resistor, and we imagine that this happens instantaneously. But when you put a capacitor in there, it takes time for the capacitor to charge. And so we talked about the voltage across the capacitor, the voltage across the resistor, and the current through the resistor. We could plot all those. And so when I first close the switch, what are all these quantities? At the instant I close the switch, before the switch is closed, but it's pretty much t equals 0. What's the state? What's the voltmeter going to read on the resistor? What's the voltmeter going to read across the capacitor? And what's the current in the circuit going to be? It's just one loop, right? So what are all those values at t equals 0?
Same voltage with the battery.
V max. And V capacitor is going to be 0.
Okay, so the voltage, let's start with the voltage across the resistor.
It's equal to the battery.
Is it 0? Is it 6 volts, or is it
6.
something else?
6.
So the voltage across the resistor is 6. How do you know that?
From previous experiments.
Okay. And what's the physical reason that that's true?
Concentration.
Static.
Voltage got equals 0.
The voltages, you want to use Kirchhoff's law.
Some of the voltages.
So the voltages around the closed loop have to be 0. And if this is 6, well, why is that 6? Why can't that be 6? Or why can't this be 3 and 3?
His lost time to charge.
Because the voltage has to go through the resistor before it can get to the capacitor.
Because of the current, isn't there
There's a lot of
least
things
time?
going on here. So let me just, this is, people are still doing this, so watch this. This is something, correct this. And I don't take it like I'm picking on you, because a lot of people are thinking the same thing. He said because the voltage has to go through the resistor before it gets to the capacitor. What's wrong with that?
I thought the voltage is static across the whole.
The voltage is across. What goes through the resistor to get to the capacitor?
Current.
Current goes through the resistor to get to the capacitor. But what does current have to do with voltage?
Voltage is equal to current times resistance.
Okay, the best way, there are multiple ways, but the best way to do this, remember that the voltage across the capacitor depends on what?
Current times the resistance.
Doesn't depend on the capacitance, because it does in a way, but that doesn't vary.
The voltage across the capacitor, sir?
Yeah, it
It has
depends
to-
on what?
How much is put into it?
Current and resistance.
How much charge is on it? If the charge is 0, what's the voltage going to be? It doesn't matter whether it's current, nothing else matters. If this is empty, the voltage is 0, period.
Yeah.
And so, this direct relationship, this is a constant. There's a direct relationship between charge and voltage, just like the voltage across a resistor. Only the resistance is constant, only depends on the current. So if you say that this is 6 volts because there's a lot of current, then I could say, well, why is there a lot of current? How do you know there's a lot of current? The best answer is this. This starts out uncharged. And so if it's uncharged, the voltage, the thing that's most clearly and undeniably and unarguably, the voltage has to be 0 because the charge is 0. And if the charge is 0, the voltage has to be 0. And why is it? Because that's how it started. And it takes time, that's what takes time. It takes time to charge the capacitor. So once you establish that this is 0, then by Kirchhoff's law, this has to be 6 volts. And if this is 6 volts, then it means the current is at its maximum value. And if we put some numbers in here, like 2 ohms and 1 farad, then this is going to be 3 amps. So this will start at 3 amps. And then you do know what happens. This will charge to 6 volts as this decays to 0 volts. And the 3 amps will follow. The voltage and the current always have to follow each other. This will go to 0. And the equations are simple. This is simply going to be I equals I max, the 3 volts, e to the minus t over the time constant, which in this circuit, the time constant depends on the R and the C. Why? Because more resistance, longer to charge. More capacitance, longer to charge. It makes sense physically. And this voltage across the capacitor, because it's charging, is 1 minus e to the minus t over the time constant RC. So there's a problem in the assignment where you start out with a field which is B max e to the minus t alpha t. So what is alpha? Alpha is just this inverted, right? The alpha could be the 1 over RC. So I could take this circuit and run it through a coil, and the current would use this to generate a field, and the current would start high, and as the current decayed, the field would go away.
Is that minus alpha t?
It's minus alpha t, yeah. Because it has to be a decaying exponential. Okay, so now what we want to do is we want to replace this capacitor with a coil. So what we just saw is an RC circuit. And we know how to deal with that, and we'll continue to review that because that will be part of what we do, circuits, between now and the end of the term and on the final exam. And the last 2 quizzes, we have 2 more quizzes after Monday. So now we're going to do, so this, whoops. This circuit with a resistor and a coil. So when we put a coil in a circuit, it's called an inductor. And that's not surprising because we know a coil, well, you'll see why in a minute. And a resistor. And so now we're doing what's called an inductor. An inductor has, like a resistor, has a property called resistance. And we define it as R equals the voltage, the ratio of voltage to current. That's our definition of resistance. And an inductor has a property called inductance. And we'll see what that is in a minute. And for that, we use the symbol L. So we use the symbol L for inductance. Okay, so let's think through, from what we know, let's think through. When I close this switch, the current starts to go through the circuit. It's got to go through the coil. So as the current goes through the coil becomes a magnet. And so if we take this coil and let's look at it this way. As the current goes through the coil, right-hand rule number 3, the current's going to circulate. We're going to introduce a flux into the coil. So here's the coil with the switch open. And when I close the switch and the current starts rising, the flux starts growing. So that's a change in flux through the coil. So a change in flux in the coil induces an EMF. So the coil gets a voltage, which we can read by putting a voltmeter there. And so unlike the capacitor, as soon as the current starts to change, the voltage appears on the inductor. Because the voltage on the inductor doesn't depend on the current, it depends on the changing flux. And if you got no flux, 0 flux, and you start adding flux, that's a big change. So the voltage across the inductor can jump right away to something very high. And what's the direction of that voltage? So the current's going through here, producing a flux that way. That's going to induce a voltage that's going to drive current which way?
Yes, correct.
Lenz's law. And we go through this a lot. Lenz's law says opposes the change. So what do we see happening? We see an increasing flux in this direction. So how do you oppose that change?
Go the opposite,
You've
go
got to
in.
prevent this from increasing. You have to, that current should produce a field or a flux in this direction. And so that tends to produce a current in the opposite direction. The induced EMF is going to oppose, what it's really opposing is the change in flux. But when you work it through, you'll see that the induced current is opposing the current driven by the battery. So that means that there's an EMF in opposition to the battery EMF. And so, opposite from the inductor, this, in the beginning, stops the current. This will immediately jump because when you go from 0 flux to some flux, that's a big change. This will jump to 6 volts. And if this is 6 volts, and this is 6 volts, then the voltage across the resistor is 0. And there's no current. Because you start at 0 and it's trying to keep it 0. So when we plot the voltage across the inductor, the voltage across the resistor, and the voltage and the current through the resistor, and for that matter, the current through the inductor, because it also goes through the inductor. The current has to start at 0. Why? Because if the current immediately jumped to some value, that would be an infinite change in flux, and it would be a big change in flux in a very short period of time. So what happens is you try to do that, this jumps to the battery voltage, and for an instant, just for an instant, stops the current. And so this goes to 6 volts. And this starts at 0 volts and starts at 0 volts. And so you might guess what's going to happen is so the current's 0, but if it just can't hold it at 0, right? Because then there's nothing changing, and if it's not changing, so the current starts to rise. And the voltage starts to rise, and the voltage across the inductor starts to drop. So, as the voltage rises, how high can it get? Well, the voltage across the inductor will go to 0 when the current becomes steady. Right? If the current through the inductor isn't changing, then there's no change in flux. And so the voltage across the resistor will go to 6 volts. The voltage through the inductor, just say this is 6 volts and 2 ohms, will go to 3 amps. And so what happens when the current is steady? When the current is steady, the coil is now full of flux, but no longer changing. So because it's no longer changing, there's no voltage here, and the entire 6 volts is on the resistor. So at the end, 2 amps of current, 3 amps of current flowing steadily through the circuit. The 6 volts is across the resistor, and the 0 volts across the inductor. So the inductor does exactly the opposite of the capacitor. The capacitor stopped the current. I mean, it allowed the current to flow freely in the beginning until the charge on the capacitor built up and stopped the current. What this does is this stops the current, really doesn't stop it, because if it stopped it, there'd be no change and there'd be no voltage. It slows the rise of current down until it reaches a final steady value. And we might expect that this is the same kind of mathematical behavior as we saw previously. So this is going to be V max, it's decaying, e to the minus t over some time constant. And this is going to be V resistor equals V max, since it's increasing, 1 minus e to the minus t over the time constant for the circuit. So the next question is, what's going to control how long it takes for the current to reach its maximum steady value and for the voltage across the resistor to get to 6 volts. So backing up a second, notice what the inductor or the coil does, is it slows down the rise of current. And it only has a voltage when the current is changing. Why? Because it only has a voltage when the flux is changing. And the flux through the coil will only be changing when the current's changing. And so it slows down the rise, but when it gets to a steady state at the end, the inductor has no voltage and no resistance. It's essentially invisible to the circuit. It's just like a piece of wire. Okay, so when we have a resistor and a capacitor, it's the resistor and capacitor that determine the time constant, right? And we said that the time constant is RC. And there's a physical reason for that, because if you have a resistance, it slows the current down and it takes longer to charge the capacitor. And if the capacitor is big, there's more capacitor to charge, so it takes longer. Okay, so how are these factors? How's the R and the L?
Negative.
So if we take a coil that doesn't have many windings, it would seem like it would have less effect than a coil with a lot of windings. So we might guess that the time constant will increase as we increase the inductance. The more windings, the more coil we have, the more it's going to produce an EMF which opposes the change, and a current which opposes the change, and that's correct. But how does the resistor affect it? Well, we're trying to change the current from 0 to some value. So if I increase the resistance from 2 ohms to 20 ohms, then the maximum current reduces from 3 amps to 0.3 amps. So because we're getting to a current which is smaller, it will actually shorten the time constant. And so the time constant for this circuit, this is like, if you're filling, it's like a smaller capacitor. It's like you're filling something. In other words, I'm gonna go from 0 to 3 amps. It's gonna take me longer than to get from 0 to 0.3 amps.
Alright, yeah.
So increasing the resistance shortens the time it takes to get to the final state.
Yeah.
And so you end up with a time constant, which is a little bit different in the other case. It's L over R. And so when you write this equation, you might see it as L over R. But since that's a compound fraction, it's often written as RT over L. And if we take the R is volts per amp. Oh, we didn't talk about L, so I can't do that yet. So what the L is it's a kind of resistance. So this will be the last thing I'll say. So resistance is a resistance to current. So it's voltage over, and the inductance is not a resistance to current. It's a resistance to change in current. It's only when the current's changing, that the flux is changing, and it produces an EMF which opposes it. So you can think of the inductance as a resistance to change in current.
What's the units for inductance?
We'll get to that on Monday, but the unit is Henry. It has a name of Henry, and it's H. And since the inductance, it's going to be volts per amp per second. So it's a resistance to change in current. Resistance is the resistance to current. Inductance, the only time the inductor opposes the circuit is if you're trying to change the current.